Now, related to the idea of conditional probability is the idea of independence. And so here's an informal definition of independence. Two characteristics, A and B, are independent if the occurrence of one does not affect the probability of the other occurring. So in everyday language, independence means that there's just no relationship between two things. That's kind of the idea of this idea of independence. Characteristics are A and B if one does not affect the other. In maybe a little more formal terms, we could define this in terms of conditional probability. So they're independent if the probability of A, given that B has occurred, equals the probability of A. This is just a formal way of saying that the occurrence of B does not affect the probability of A. Likewise, we could describe this as saying the probability of B, given that A has occurred, equals the probability of B occurring. So again, we're saying that the occurrence of A has no effect on the probability of B occurring. Okay. So to illustrate this idea, let's look at example 5.6 from the book, which gives some results from this prostate screening test. Now these numbers here are a little bit different than the example that we saw before, but it's the same interpretation. We've got 120 guys. They take the test. They have either a low, moderate, or high risk. They either have cancer or they do not have cancer. And so we might ask, is the risk category related to having cancer? You would think that if you have a low test risk, then you should have a lower chance of getting prostate cancer. If you have a high risk, then you should have a high probability of having prostate cancer. Well, is that the case? Well, we can start to answer this by calculating conditional probabilities and looking for independence. So first, let's just calculate the probability of having cancer. So in this population of men, we have a total of 20 who have prostate cancer, divided by the total population size 120, so 0.167. So we got about 16.7% of guys in this population that have cancer. Now let's calculate the conditional probability of having cancer given that you have a low risk. So the denominator is going to be the number of guys in the low risk category, which is 60. The numerator is going to be the number of those guys who do have cancer, which is 10. 10 divided by 60 is 0.167. And so the thing to observe here is that this conditional probability is equal to the probability of having cancer. So that means that the fact that you were in the low risk category had no effect on your probability of having cancer. So what this illustrates is that having a low risk, this category, or this characteristic, is independent of the characteristic of having cancer. There's just no relationship between being in this low risk category and having cancer. Okay. Likewise, let's look at this conditional probability of having cancer given that you're in the moderate category. And so if you're in the moderate category, there's 36 people. Out of those, 6 have prostate cancer, so 6 divided by 36 is also 0.167. So again, we see that this conditional probability equals the probability of having cancer. So the fact that you're in the moderate category doesn't affect your probability of having cancer. So in other words, this characteristic of moderate risk is independent of the characteristic of having cancer. One last conditional probability. Let's calculate the probability of having cancer given that you're in the high risk category. So there's 24 guys in the high risk category. 4 of them developed cancer. 4 divided by 24 is 0.167. And again, we see that these two probabilities are the same. Probability of having cancer, given that you're in the high risk, equals the probability of having cancer. So being in the high risk category did not affect your chances of getting cancer. So having a high risk is independent of having cancer. So what this illustrates, what this means in kind of the big picture, is that the risk category is independent of having cancer. there's just no relationship between the risk category and having cancer. So there's no relationship between the category and having cancer. So what does that mean in even more practical terms? Well, it tends to indicate that the test isn't any good. We showed that there's just no relationship between the category that you're in and your chances of having cancer. So this means that this test just wasn't worthwhile giving. It doesn't give you any new information. All right, our last concept here is what's called Bayes' theorem. Bayes' theorem is an extremely important result in the field of statistics called Bayesian statistics, which you may have heard of at one point or another. Now, we're not going to get into Bayesian statistics in this class, but we do want to familiarize ourselves with the basic idea of Bayes' theorem. Bayes' theorem, as we're going to see here in our next example, is very useful in analyzing the results of drug tests. So Bayes' theorem, here's a very simple form of Bayes' theorem. Bayes' theorem is a way of calculating a conditional probability. The probability of characteristic A given that B has occurred equals the probability of B given that A has occurred times the probability of A divided by the probability of B. Okay. So what can we do with this? Well, let's look at this example 5.8 from the book. Consider a certain test for a disease. Now what the disease is and what the test is isn't terribly important for our purposes. And let's suppose that a patient tests positive and they want to know what's the probability that they actually have the disease. Now, we'd like to think that this probability is 1 or 100%, but tests for diseases are not perfect. As we've seen before, there's a possibility of false positives or false negatives. So this probability should be 1, but it's not. Okay. So let's suppose that for this particular disease, the prevalence is 0.2%. So that means that 0.2% of people have the disease, or in terms of probability, the probability that a randomly selected person has the disease is 0.002 when you convert this percentage over to a proportion or to a decimal. Okay. Let's also suppose that the sensitivity of this test is 85%. So remember, sensitivity is the conditional probability of testing positive given that you have the disease. So that probability is 0.85. Let's also suppose that for this certain disease, or this certain test, that it gives positive results 8% of the time. So that means that if we just randomly select a person, the probability that they test positive is 0.08. Okay. So we want to know the probability of, well, let's look at this part. We want to know the probability of that we have the disease given that we have tested positive, okay, which has this general form as given in Bayes' theorem. So A is the characteristic of having the disease, B is the characteristic of testing positive. And so using Bayes' theorem, this conditional probability is the probability of testing positive given that we have the disease. So this is B given A times the probability of A, which is the probability of having the disease, divided by the probability of B, which is the probability of testing positive. And so now these three probabilities on the right we were given in the problem. And so now all we need to do is plug things in. Probability that we have the disease given that we've tested positive, 0.85 divided or times 0.002 divided by 0.08, and then we do that arithmetic and we get 0.021. So that's the probability that you have the disease given that you have tested positive. Alright, so let's talk briefly about what this conditional probability means. The probability of having the disease given that we test positive is 2.1%. So we can interpret this as saying that a positive result means that there's a 2.1% chance that the patient has the disease. Okay? Well, that may be a little bit disturbing. We would think that if the tests were really good, then this probability should be close to 100%. If you test positive, you would think that that means that you do have the disease, but this shows that there's really not a very good chance that you have the disease, even if you test positive. So let's make another observation here. If the test was not given, the chance that the patient has the disease is 0.2%. That's what we were told in the problem, that 0.2% of the population has this disease. So if you don't have the test, here's your chance of having the disease. But if you do get the test and get a positive result, this is your chance of getting the disease. So getting a positive result doesn't really increase the chance of having the disease by all that much. So getting a positive result does not increase the chance that the patient has the disease by all that much. It goes from 0.2% up to 2.1%. Now whether that's a big increase or not is maybe debatable, but it's arguably not as much as we would like. And so this begs the question, is the test really worth it? Just because we get a positive result doesn't really increase the chance that we have the disease by all that much. So that's maybe a debatable question. Is the test really worth it? The point here is just to illustrate how Bayes' theorem can be used to calculate conditional probabilities in cases such as this.